Hello, my name is PRibeiro and I'm a PhD student at Instituto Superior Técnico, University of Lisbon in Portugal. I'll be presenting my work, 2D application-ready magnetoelastic cilia tactile sensing device, developed in collaboration with INESC-MEN and ISR in Portugal and the ARQ at Queen Mary University of London in the United Kingdom. A wide variety of tactile receptors is found in biological beings. These organelles found in nature can provide a source of inspiration for novel tactile sensing devices. The ciliary structure is one of these. Commonly found in insects and mammals for sensing purposes, this structure excels at detecting small fluid flows, forces, and surface textures. The high sensitivity of this topology could be interesting for some industrial robotic applications, as well as medical robotic applications. The ciliary structure consists in a combination of two organelles, a passive organelle known as cilium and an active organelle known as dendrite. When the cilium is activated, the dendrite sends a neuronal signal to the brain. The device we developed mimics this biological structure, with the cilium being an elongated flexible cylinder with embedded magnetic particles, and thus possessing a permanent magnetization. This is placed over a 2D magnetic sensor, which will detect the magnetic signal generated by the magnetic elastomer, transducing it into a resistance variation proportional to the cilium deformation. The used magnetic sensor is a 2D monolithic TMR sensor with two Wheatstone bridges in parallel, one for X direction and another for Y direction sensitivity, sharing the same power supply. The chip was achieved by depositing 4 stacks with different sensitive directions in the same piece of silicon. The sensitive orientation of the stack is defined at the time of deposition, and since this stack makes use of an alumina barrier and top pin configuration, it presents magnetoresistance without requiring thermal annealing. On the plot shown on the right, you can see the characteristics for X and Y sensitive directions for one of these chips. As mentioned before, the cilia are produced as a magnetic elastic composite, being flexible while presenting a permanent magnetization. This composite consists in a mixture of 35% PDMS and 65% neodymium iron-boron particles in a mass proportion, and is produced using a molding technique. The first step in this molding is to create a 35 micrometer thick clear PDMS membrane by spin coating PDMS over a sacrificial glass substrate. Then, an aluminium mold is placed on top of a PDMS membrane and magnetic PDMS is poured over the mold and placed under a vacuum to fill the voids inside it. This magnetic elastic PDMS is left to cure, and the composite is thermally annealed at 135 degrees Celsius for 90 minutes under a 1 Tesla magnetic field applied in the axial direction of the cilia. The mold is released and the cilia are detached from the sacrificial substrate. Finally, the cilia undergo an oxygen plasma treatment and are bonded to the sensor, which is passivated with a silicon oxide layer. The resulting composite was measured using squid magnetometry and found to have a 50 EMU per centimeter cubed magnetic remanence. The sensor tested in this work possesses a single cilium centered over the TMR sensor, with 3 mm of height and 400 micrometers of diameter. The chip is mounted on a PCB, which is in turn mounted over a brass connector, for added robustness and easy interchangeability. In this short video, you can see a demonstration of the finished device working in the two sensitive directions when the cilium is manually actuated. We have also developed a multiphysics simulation to predict the behavior of the cilia sensor. The simulation is composed of 3 models that fit forward into each other to produce the cilia sensor complete system simulation. First, a finite element method simulation using COMSOL is made to estimate the deformation of the cilium given a certain prescribed indentation. The results of this deformation are then exported to a custom C++ code that will estimate the cilium volume magnetization locally by discretizing it into magnetic dipoles. The orientation of each dipole is estimated by assuming the cilium pillar can be discretized into infinitesimally thick planes that can translate and rotate but not deform themselves, and that the magnetic dipoles existing within these planes are always normal to it. It is assumed that the cilium is uniformly magnetized. Finally, once the volume magnetization has been estimated, the magnetic field over the sensor surface is computed by adding the magnetic field contribution of each dipole over each area element of the sensor surface. The final result is the magnetic field area distribution over the sensor surface, which can then be averaged out to estimate the expected sensor signal, given its sensitivity has been obtained experimentally. This also provides a very powerful tool for sensor and application designers to assess if and what cilia configurations best suit their required specifications. Given the 2D sensitivity of the underlying magnetic sensor, it should be possible to determine the cilium deflection and tilting angle simultaneously. To characterize the sensor electrical behavior versus these two quantities, a characterization setup was assembled. The setup consists in a 3D motorized Cartesian stage. The 3-axis motors are encoded and it is therefore possible to know the distance traveled in each axis. Assembled above the sensor is an acrylic class table. On top of this, a camera phone records the cilium deformations. The stage will then be manipulated to reach a prescribed displacement and angle. The imposed displacement is obtained through the encoder steps of the z-axis, while the angle is obtained through the image of the cilia captured by the camera. The testing sequence is as follows. First, the z-axis is moved to bend the cilium up to a prescribed displacement. Then, the xy axes are moved to orient the cilium to a given angle. The cilium is rotated into various set angles, with a photo and a recording of the TMR x and y signal being taken. Angles are taken until a full rotation has been performed, after which the cilium is displaced by a further 100 micrometers, and the rotation process begins again. From the acquired signal for both components of the sensor, it can be observed that there is a clear increase in magnitude as cilium displacement increases. Furthermore, as the cilium rotates, there is a sine-cosine characteristic of the two axes, suggesting that the angle could be obtained through a trigonometric function. To obtain the cilium tilting angle from the sensor signal, one can assume the x and y characteristics of this signal will be a circle. Therefore, the angle may be computed as the arctangent of the quotient between the y and x voltages measured by the sensor, which are related to the I and x magnetic fields on the sensor surface. The angle computed in this manner was compared to the one obtained through the deformed cilium photos, with the average error and coefficient of determination being computed as shown. An angular precision of 6.1 degrees was observed, corresponding to 1.6% of a full rotation. From a previous study, we had already empirically observed that the voltage measured at the sensor terminals was a function of a linear combination between a logarithmic and a linear function of the cilium displacement. However, we want the opposite, cilium displacement as a function of voltage, and therefore we must invert this equation. Although non-trivial, an inversion of this function does exist, the Lambert W function. The function describing the cilium displacement versus the voltage magnitude is shown at the bottom. Finally, to obtain the cilium displacement as a function of x and y voltages, the voltage magnitude can be described by an ellipse equation, as the x-axis sensitivity is slightly different from the y-axis sensitivity. The previously mentioned deformation equation with the inserted elliptical equation for the voltage magnitude yields a surface. The surface was fitted to the experimental data and found to fit with the coefficient of determination of 99.87%. Furthermore, the root mean square error of the fit was 15.21 micrometer, while the maximum error was of 202 micrometers, thus proving that this model fits the sensor behavior in what concerns the cilium displacement. In conclusion, a 2D bio-inspired cilia tactile sensor was developed and characterized. The device is composed by a 2D monolithic TMR sensor in Wheatstone bridge configuration and a thin magnetic and elastic cilia placed on top. A simulation model was developed to estimate the sensor behavior, given its geometry and magnetic elastomer characteristics. For cilium displacement angles, we were capable of inferring the cilium angle through a trigonometric relationship, with an average angle determination error of 6.1 degrees. For cilium magnitude, we proposed a 2D model to obtain the cilium displacement through the x and y voltages measured by the sensor, and this model fitted with the experimental data with a root mean square error of 15.21 micrometers. Thank you.